Question 4, you've already done a question like question 4. You did it for the midterm. So the guys in 2004, they were doing. So these 4 yokels had a numerical problem like the one that you had on the midterm. So the information that they were given was not, for their exam, they were not given X and Y to start with. Instead, they were given the same kind of information that you got on your midterm question. So when I made up the key, I wanted to show them where all the cross product matrices had come from. So they were given X transpose X and they were given X transpose Y. They had to figure out X transpose inverse. So they were also given Y transpose Y. Compute the least squares coefficient estimates. That's just memory work. If you're given this piece, or you derive this piece, you're given this piece, you certainly can get the least squares estimates. Compute an estimate of the error variance. So the residual sum of squares is 93. And so we know that sigma hat squared is that residual sum of squares over the degrees of freedom, and we could get either the ordinary least squares estimate of the error variance or the maximum likelihood. All the changes is the term of the denominator. Compute an estimate of the coefficient covariance matrix. Well, we've already got sigma hat squared, and by this point we've already calculated X transpose X inverse, and so it's a pretty simple matter of plugging the numbers in and grinding away. Test the null hypothesis that beta 1 equals 0 at the 10% level. So I just, in order to do this, I introduced a little index so that I could do all the t-tests at once. And so the t-statistics for all the different coefficients are here on the left for both OLS and ML formulations, and so it doesn't look like we reject any of the null hypotheses. I think that was the end of the other question. Test the null that beta 1 and beta 2 are both 0. Not equal to another, but so you're not taking a difference between them, but that they are both 0. So it's a joint test. So the restriction matrix R would be the identity matrix, and the restriction vector r would be just 2 zeros. And so the general formulation of the, again, there are all kinds of different ways to construct F statistics. You have the residual sum of squares under the unrestricted model minus the residual sum of squares under the unrestricted model divided by the number of restrictions all over RSS big omega divided by, usually we use n minus k as the degrees of freedom. You could use n if you have a really big sample. And so the trick in this part of the exercise was to try to recall all the different ways you can represent residual sums of squares. So under the null hypothesis where beta 1 and beta 2 are 0, you have a model in which there's nothing but an intercept. So for example, in the model where there's nothing but an intercept, you pick up X transpose Y, you pick up the 0th row there. That's what the 0 came from. So some of the indexing on here has to do with addressing certain cells in MathCAD. So this is the residual sum of squares when you constrain the two slopes to be 0 and allow only the intercept to differ from 0. And then the other part is the residual sum of squares given the information that you had available to you, the residual sum of squares when there is just, when all 3 explanatory variables are on the right-hand side. I could run a different version of the same problem. Another construction would be, that's the same F statistic. Well, big R is the restriction matrix, little r is the restriction vector, and RSS big omega is still the residual sum of squares under the alternate hypothesis or the full model. And so when you're reviewing, you want to don't try to remember all the different ways of constructing F-tests from data that you might, manipulated data that you might be given, the matrices of cross products and so on and so forth. Yes? Yes. It's got to be less than K. Less than K. No. No. When you learned about F-tests in your very first regression class, you always worked with a null hypothesis that all of the slope coefficients were 0. And that's because they didn't want to confuse you or complicate matters too much. But we know now that we can go way beyond that. We can do all kinds of things. So that just happens to be one specific example of an F-test. That's why when we went over this in class, I tried to give it to you as a very general representation in which you could fit all F-tests.
So in this case, it was beta 0 equals beta 1 equals beta 2 equals 0. So,
in this case, it should be K minus 1 or 2, right? In this specific example, it is 2. And since there are 3 right-hand side variables, 2 is equal to 3 minus 1. So in this very specific example, you are right. Only because there was some limitation to the amount of computation I could have people do in class. Like I could have had 4 right-hand side variables and say, conduct a test about 2 of them. Or like the translog homework where we had those symmetry and equality restrictions, I could have said, instead of doing individual t-tests, I could have said, let's do all the tests as a group, as an F. And that certainly is not K minus 1. Instead there were, I think we said there were 6 symmetry restrictions, and there were 5 equality restrictions, or 11. Explain the test for heteroskedasticity. Well, that was the test taker's choice. So all I did was provide a little rubric for what I was looking for in answers. So whatever heteroskedasticity test you wanted to describe, you had to tell me the name. You had to give me a detailed procedure that included the statement of the null, statement of the test statistic, and the prescriptive steps to take upon rejection of the null. That is, if you reject the null of no heteroskedasticity, what comes next?